A single teaspoon of it would weigh about 1 billion tons, not 1 billion pounds. 1 billion tons, a small mountain balanced on a piece of cutlery, and it lives at the center of a star you could drive across in 20 minutes. That is the substance we are going looking for tonight, and the strange part is that nobody on Earth knows exactly what it is. As you fall toward the center of a neutron star, matter breaks down floor by floor. Atoms come apart. Then nuclei. Then the neutrons themselves. And right at the bottom waits a question our deepest physics cannot answer. So get comfortable, settle in, and let us fall all the way down together to find out. Part 1. The city-sized question mark. I want you to imagine holding a single teaspoon. It is an ordinary teaspoon, the kind you stir sugar with, light enough that you forget it is in your hand. Now imagine filling it just once with material taken from the center of a neutron star. The moment you did, that teaspoon would weigh about 1 billion tons, not 1 billion grams, not 1 billion pounds. 1 billion tons, which is roughly the weight of a small mountain or of every car and truck and bus humanity has ever built, balanced on the end of a piece of cutlery. You could not hold it. Nothing you have ever touched could hold it. It would fall through the spoon, through your hand, through the floor, through the planet, because there is nothing in your everyday world dense enough to get in its way. That is the substance we are going to go looking for tonight. And the strange thing, the thing that makes this one of the most quietly astonishing objects in all of physics, is that this billion-ton spoonful does not live inside something enormous. A neutron star is small. You could drive across one in about 20 minutes on a quiet highway. It is roughly the width of a city, somewhere between 20 and 24 kilometers from one side to the other. A sphere you could lay across a single metropolitan area and still have room to spare. And yet packed into that city-sized ball is more mass than the entire Sunday. Take the sun with its million Earth bulk and crush it down until it fits between the suburbs of a single town, and you begin to get the idea. So here is the question that the whole of tonight rests on, and I want to put it to you plainly before we begin, because everything that follows is an attempt to answer it. What is actually down there? What happens to matter, to ordinary matter, the stuff of your hands and the chair you are sitting in when you squeeze it that hard? Because matter does not stay the same under that kind of pressure. It cannot. The rules that hold it together, the quiet agreements between particles that let an atom be an atom and a nucleus be a nucleus, start to fail. And they do not all fail at once. They fail one after another, like floors collapsing beneath you in a very tall building, each floor dropping you into a deeper and stranger place than the one before. That is the real shape of a neutron star. It is not one substance. It is a stack of floors, and each floor down is matter that has been crushed past the point where the floor above it could survive. Tonight we are going to fall through those floors together, slowly, patiently, from the surface all the way down toward the center. And as we fall, we are going to watch matter forget what it is. We are going to watch the atom come apart. Then we are going to watch the nucleus come apart. Then, deeper still, we are going to watch the neutron itself, the very particle this kind of star is named for, begin to dissolve into something that has no name in ordinary language. And right at the bottom, in the final room, we are going to run into a wall. Not a physical wall, a wall in our knowledge. Because the center of a neutron star is the single place in the entire present-day universe where our deepest theory of how matter is built simply stops working, the math goes quiet, the equations stop giving answers. The deepest interior of a neutron star is, right now, tonight, a blank space the size of a city. Let me say that again, because it is the core of everything. We have telescopes that can read the chemistry of galaxies 13 billion light-years away. We have detectors that can feel a ripple in space itself smaller than the width of a proton. We have mapped the first faint glow left over from the birth of the cosmos. And yet there is a region a few kilometers wide, at the core of an object we can point to in the sky, whose contents we genuinely cannot calculate. It is one of the last truly sealed rooms in nature, and it is hiding in plain sight inside some of the most studied objects in astronomy. I find that a beautiful thing to sit with. We tend to assume the mysteries left in physics are all unimaginably far away or unimaginably small, out past the edge of the observable universe or down beneath the scale of the atom. But this one is neither. It is a specific place. It has a location. You could, in principle, fly there. And if you did, and if you could survive the journey, which you absolutely could not, you would be falling toward a piece of the universe that no equation we possess can describe. The closer you got to the center, the less anyone on Earth could tell you about what was around you. So this is a descent into the unknown in the most literal sense I can offer you. We are going to fall, floor by floor, and at each floor I am going to tell you exactly what we think happens to matter there, and how confident we are, and where the certainty runs out. And the certainty does run out. That is the promise of tonight. We will go as far as human knowledge can currently go, and then we will stand together at the edge of the part nobody knows and look down into it. There is one more thing I want to plant in your mind before we step onto the surface, because it is the strangest turn in the whole story, and I want you to be watching for it as we descend. You might expect that as matter is crushed harder and harder, it would become more chaotic, more broken, more like a mush. That is the intuition. More pressure, more mess. But that is not what happens. As we fall deeper into a neutron star, the matter does break down, yes, in the sense that atoms and nuclei and neutrons lose their identities. But at the same time, it becomes more ordered, not less. It organizes itself into some of the most perfectly structured states of matter that are theoretically possible to exist anywhere. The most broken matter in the universe may also be the most exquisitely arranged. Hold on to that contradiction. It is going to come back, all the way at the bottom, in a form stranger than you are expecting. So settle in, get comfortable, however you like to be, when you let a long story carry you off. This is going to be a slow fall, and there is no hurry at all. We have a whole star to sink through, and we are going to take our time with every layer of it. But before we can fall in, we need to understand something first. We need to understand how nature builds a trap this tight in the first place. Because the way a neutron star holds itself together is not what most people think it is, and the usual explanation, the one you will find in a lot of textbooks, is quietly, importantly wrong. And the truth of how it holds together turns out to be the same truth that explains why the center is such a mystery. So that is where we go next, up out of the depths for just a moment, to watch one of these objects being born. Is less than break time equals 1s is greater than number. Part 2. How you build a trap this tight. To understand a neutron star, you have to understand that it is a corpse. It is what is left behind when a giant dies. And the death is one of the most violent events the universe is capable of producing. It begins with a star far larger than our sun, somewhere between about 8 and 20 times the sun's mass, maybe more. For most of its life, that giant star does what every star does. It fuses light elements into heavier ones in its core, and the energy pouring out of that fusion pushes outward, holding the star up against the relentless inward pull of its own gravity. It is a balance, a standoff, a war between two enormous forces that lasts for millions of years. Gravity pulls in, fusion pushes out. As long as there is fuel to burn, the standoff holds. But fuel runs out. The star fuses hydrogen into helium, then helium into carbon, then onward through heavier and heavier elements, each stage faster than the last, until finally it builds a core of iron. And iron is the end of the road. You cannot get energy by fusing iron. Iron is the ash of the cosmic fire, the point at which fusion stops paying its own way. So when the core of that giant star becomes iron, the outward push vanishes almost instantly. The fire goes out. And for the first time in the star's entire life, gravity has no opposition. What happens next happens fast. Faster than you can really picture. The iron core, which is roughly the size of the Earth, collapses. And it does not collapse over years or hours or even seconds. It collapses in a fraction of a single second. A ball of iron the size of our planet falls inward on itself and is crushed down to the size of a city in less time than it takes you to blink, with the infalling material reaching a substantial fraction of the speed of light. The temperatures and pressures during that collapse are beyond anything else in the modern universe outside of a black hole. And then the outer layers of the star, the enormous envelope of gas that had been sitting on top of that core, come crashing down onto the suddenly tiny, suddenly rigid center, and they rebound, and they detonate outward in the titanic explosion we call a supernova, an explosion so bright it can briefly outshine an entire galaxy of hundreds of billions of stars. When the light of that supernova fades, sometimes, not always, but sometimes, something is left behind at the very center, the crushed core, the thing that did not blow away, and that thing is a neutron star. Now, to understand what is holding that core up, why it stopped collapsing at all instead of continuing all the way down to a black hole, we need to talk about one of the deepest and strangest rules in all of physics. It is a rule about how the smallest particles behave when you crowd them together, and it has a name that sounds intimidating but describes something beautifully simple. It is called the Pauli exclusion principle. Here is the idea. Particles like electrons and neutrons are, in a sense, intensely private. Each one occupies its own quantum state, its own particular description of where it is and how it is moving. And the Pauli exclusion principle says that no two identical particles of this type can ever share the exact same quantum state. They simply refuse. It is not that they push each other away with a force in the ordinary sense, the way two magnets repel. It is something deeper and stranger than that. It is a rule written into the basic grammar of reality, a law that says these two things cannot be in the same situation at the same time, full stop. And this has a remarkable consequence. When you try to crush a cloud of these particles together, when you try to force them all into the same small space, they resist. Not because they are hot, not because they are moving fast in the way a hot gas does, but purely because they are running out of available quantum states to occupy. As you squeeze them, they are forced into higher and higher energy states, faster and faster motion, simply to keep from sharing. And that resistance, that refusal to be crowded, produces a pressure. We call it degeneracy pressure. And it is a pressure that does not care about temperature at all. It would push back just as hard at the coldest temperature imaginable. It is pure quantum stubbornness, made structural. This is the force that holds up a white dwarf, the corpse left behind when a smaller star like our Sun dies. In a white dwarf, it is the electrons that refuse to be crowded, and their degeneracy pressure holds the whole dead star up against gravity. But there is a limit. There is always a limit. If you pile too much mass onto a white dwarf, more than about 1 4/10 times the mass of our Sun, a threshold we call the Chandrasekhar limit, then even the electron's refusal is not enough. Gravity wins. The electrons get crushed so hard that they are forced into the atomic nuclei themselves, where they merge with protons and turn them into neutrons, in a process with the rather dry name of inverse beta decay, though I prefer to think of it as the moment the atoms surrender. The electrons are gone, swallowed, and what is left is a sea of neutrons. Now a new line of defense takes over. The neutrons themselves, being the same kind of intensely private particle, also refuse to be crowded. Neutron degeneracy pressure, far stronger than the electron version because neutrons are so much heavier, rises up to hold the line against gravity. And this is the standard textbook story of what a neutron star is. A ball of neutrons, held up by their own refusal to share quantum states, frozen forever in a standoff against their own crushing weight. And here is where I have to tell you that the standard story is not quite right. This is the part that most people never hear, and it matters enormously for everything we are about to explore. Neutron degeneracy pressure, on its own, is not actually strong enough to hold up the neutron stars we observe. If pure neutron degeneracy were the only thing fighting gravity, the heaviest a neutron star could possibly be would fall well short of the masses we actually measure in the sky. We see neutron stars out there weighing more than 2 times the mass of the Sunday. Degeneracy pressure alone could never support that. So something else, something stronger, must be doing most of the work. That something is the strong nuclear force. The strong force is the most powerful of the 4 fundamental forces of nature, the force that binds quarks into protons and neutrons, and binds protons and neutrons into nuclei. And at very short range, when you push nucleons extremely close together, the strong force becomes fiercely repulsive. It pushes back, hard, against any attempt to squeeze the neutrons closer. And it is this repulsion, this short-range shove from the strong force, that does most of the real work of holding a neutron star up. The neutron's refusal to share is part of the story, but the strong force is the muscle. Now hold on to this, because it is the thread that runs through everything tonight. The strong force holds the neutron star up, and the strong force is exactly the thing that we believe begins to break down at the very center, where the pressure is highest of all. The force that supports the whole structure may itself be coming undone in the deepest room. That is why the center is the mystery. We are asking what happens to the very thing the star is leaning on, and there is a final rung on this ladder, a last threshold beyond which nothing known can save the star. If you keep adding mass, somewhere around 2¼ times the mass of the Sun, give or take, you reach a point called the Tolman-Oppenheimer-Volkoff limit. Past that limit, no pressure that physics knows about, not degeneracy, not the strong force, not anything, is enough to resist gravity. The star collapses through every floor at once, all the way down, and becomes a black hole. So a neutron star lives in a narrow window, balanced between the white dwarf below it and the black hole above it, holding itself together by a combination of quantum stubbornness and the most powerful force in nature, right at the edge of total collapse. That is the trap. That is how nature builds something tight enough to crush a teaspoon into a mountain. And now that we understand how the trap holds, we can finally step onto its surface and begin to fall. Because the first breakdown, the first floor giving way beneath us, is waiting in the very first few millimeters of the descent, before we have gone any distance at all. Is less than break time equals 1s, is greater than number. Part 3. The surface and the first breakdown. Let us stand on the surface then, in our imaginations, where no real thing could ever stand. The first thing you would notice, if noticing were possible before you were instantly destroyed, is the gravity. The surface gravity of a neutron star is somewhere around 100 billion to 200 billion times the gravity you feel right now. That number is so large it stops meaning anything, so let me make it physical for you. Imagine holding a single marshmallow 1 meter above the surface and letting go. On Earth it drifts down and lands with a soft, silent nothing. On a neutron star, that marshmallow would fall 1 meter and strike the surface moving at thousands of kilometers per second, and it would hit with the energy of a substantial bomb, a marshmallow, dropped from the height of a tabletop. That is the gravity we are standing in. That gravity does something remarkable to the shape of the star. It makes it almost perfectly smooth. On Earth, mountains can rise 9 kilometers above sea level, because Earth's gravity is weak enough to let rock pile that high. On a neutron star, the gravity is so ferocious that nothing can stand tall. The highest mountains, on a neutron star's surface, may be no more than a few millimeters high. Think about that. The entire surface of this object, a sphere the size of a city, is smoother than anything human beings have ever manufactured, smoother than the finest polished mirror, with its tallest peaks shorter than a grain of rice. It is the smoothest large surface that nature is known to build anywhere. Above that surface sits a wisp of atmosphere, though calling it an atmosphere is almost generous. It might be a meter thick. It might be only centimeters. It is a thin skin of plasma, mostly the lightest elements, hydrogen and helium and perhaps carbon, held in a layer so thin and so compressed that the whole thing would be invisible to you. And yet that thin skin matters enormously because it is the part we can actually see. When astronomers point an X-ray telescope at a neutron star, an instrument like NICER, which sits aboard the International Space Station and watches these objects with exquisite precision, it is reading the faint thermal glow coming off this thin envelope. From that glow, from the precise way the light is shaped and shifted, scientists work backward to measure the star's mass and its radius. Everything we know about the inside, every constraint we have on the mysteries waiting below, begins with reading the light off this paper-thin skin. We are detectives standing outside a sealed building, studying the warmth leaking through the walls. Now let us push down through that skin, into the outer crust, and watch the first floor of matter give way. Because here, in the outermost solid layer of the star, the atom, as you know, it ends. On Earth, an atom is a tidy thing. A dense nucleus of protons and neutrons sits at the center, and around it, at a comfortable distance, electrons orbit in their shells, a whole cloud of negative charge defining the atom's size and its chemistry. Almost all of an atom is empty space, the enormous gap between the tiny nucleus and its distant electrons. That emptiness is what gives ordinary matter room to be squeezed. And in the crust of a neutron star, it is being squeezed mercilessly. The pressure here is so enormous that the atoms can no longer hold onto their electrons. The neat orbits collapse. The electrons are torn away from their parent nuclei entirely, and they delocalize, which is a careful way of saying they stop belonging to any one atom and instead flow freely through the whole structure as a single shared sea of negative charge. What is left of the atoms, the bare nuclei, settle into a rigid, orderly crystal lattice, a regular three-dimensional grid, locked in place by their mutual repulsion and held together by the pressure all around them. And through that grid of nuclei, the freed electrons race, a degenerate sea so dense and so energetic that the electrons themselves are moving at nearly the speed of light. This is the first breakdown. Flaw 1 has given way. The atom, that fundamental unit of chemistry, that thing you learnt about as the basic building block of all ordinary matter, no longer exists here as a discrete object. You cannot point to an atom in the crust of a neutron star, because the electrons that would define it have all run off to join the common sea. What you have instead is something like a metal beyond any metal, a crystalline lattice of atomic nuclei suspended in an ocean of free-flowing electrons, conducting electricity and heat in ways that put any earthly conductor to shame, at a density where a single thimbleful already outweighs anything you own. And as we sink deeper into this crust, the matter keeps changing. Remember that the crushing pressure keeps forcing electrons into protons, turning them into neutrons. So the deeper we go, the more neutron-heavy the nuclei become. Near the top of the crust, the nuclei might be ordinary iron, 26 protons each. But as we descend, the nuclei grow heavier and stranger and more bloated with neutrons, swelling with far more neutrons than any stable atom could ever hold up here on the surface of the Earth. They become nuclei that simply cannot exist in any laboratory, that would fall apart in an instant in our world, but that are held together perfectly well down here by the immense pressure pinning them in place. We are already looking at forms of matter that exist nowhere on Earth, that could not be made to exist on Earth, and we have only just begun. We are still in the outermost shell. We have fallen, in the scale of the whole star, almost no distance at all. It is worth dwelling on why the atom is so fragile under pressure, because it explains the whole first stage of our descent. An atom, for all its importance, is mostly nothing. If you scaled a single atom up so that its nucleus was the size of a marble and placed that marble at the center of a large stadium, the electrons would be flitting around somewhere out near the highest seats, and everything in between, the entire volume of the stadium, would be empty. That is what ordinary matter is. A few specks of substance surrounded by enormous halls of empty space. And empty space is exactly what gravity, given enough mass, can squeeze out. The crust of a neutron star is what you get when all that emptiness has been wrung from matter, when the electrons have been pressed down out of their distant orbits and forced into the common sea, leaving the nuclei packed far closer together than they could ever sit in any earthly solid. The atom does not break down because it is destroyed by some violent blow. It breaks down because its emptiness is taken away, and without its emptiness, it can no longer be an atom at all. And that gives you a way to understand the entire descent in advance, a single thread to hold as we fall. Each floor we pass through is the removal of another kind of emptiness, another margin of space that matter was using to keep its structure. The crust removes the emptiness inside atoms. Deeper down, the pressure will remove the emptiness between nucleons, forcing them to touch. And at the very bottom, it may remove the last emptiness of all, the space inside the neutrons themselves, where the quarks have always had a little room to move. The whole journey to the center of a neutron star is, in a sense, a single long process of emptiness being squeezed out of matter, layer by layer, until there is nowhere left for anything to hide. I want you to feel how quickly this happened. We stepped onto a surface smoother than glass, pressed down through an atmosphere thinner than a sheet of paper, and within the first few 100 meters, the atom itself had already dissolved. The most basic unit of chemistry, gone, in the first stretch of the descent. And the density here, as staggering as it already is millions of times less than what waits at the center. We have so much further to fall. The floors below are stranger than the one we just passed through, and the next one is perhaps the strangest solid that physics has ever imagined, a material so bizarre that the scientists who study it had to reach for the language of the kitchen to describe its shapes, and so strong that it may be the toughest substance anywhere in existence. Just below us, the nuclei themselves are about to start forgetting what shape they are supposed to be. Is less than break time equals 1s is greater than number part 4, where nuclei forget their shape. We are crossing now into the inner crust, still only about a kilometer down in total if you count the whole crust together, a layer that holds only around 1% of the star's entire mass, and yet contains some of the most extraordinary physics in the cosmos. And the first thing that happens as we enter it is that the neutrons begin to escape. Up in the outer crust, the neutrons were all bound inside nuclei, tucked away with the protons. But as the pressure mounts, the nuclei become so swollen, so overstuffed with neutrons, that they can no longer hold them all. The neutrons start to leak out. Physicists call this neutron drip, which is a wonderfully vivid name, because that is almost exactly what it is. Neutrons begin to drip out of the nuclei and into the spaces between them, until the whole region is filled with a sea of free neutrons, flowing around and through a lattice of nuclei that are still, for now, holding their ground. And these free neutrons do something remarkable, something we will see more of as we go deeper. They become a superfluid, a quantum liquid that flows with absolutely no friction at all. But let us hold that thought for a moment, because something even stranger is happening to the nuclei themselves. To understand it, you need to picture the war that is being fought inside every nucleus. There are two forces in tension. The strong nuclear force pulls all the protons and neutrons together, trying to clump them into a tight ball. That is why nuclei are normally round, little spheres, because a sphere is the most compact shape, the one that lets the strong force pull everything as close together as possible. But the protons in the nucleus all carry positive charge, and like charges repel. So there is also an electrostatic force pushing the protons apart, trying to spread them out. Under normal conditions, the strong force wins easily at short range, and the nucleus stays a tidy sphere. But down here, in the inner crust, packed so tightly that the nuclei are nearly touching, the balance shifts. The two forces come close to a draw, and when they do, the matter starts to rearrange itself into shapes you would never expect. This is the realm of what physicists, with a sense of humour I deeply admire, have named nuclear pasta, because as the balance between attraction and repulsion shifts with depth, the nuclear matter stops being round and starts taking on the shapes of an Italian kitchen. First, the nuclei merge into little blobs that scientists call gnocchi. Press deeper, and those blobs stretch and fuse into long cylinders, rods of nuclear matter, which they call spaghetti. Deeper still, and the rods flatten and merge into broad sheets, layers of dense matter, stacked like pages, which they call lasagna. And then it inverts. Go further, and you find the same shapes in negative, as it were, with tubes of empty space running through solid matter, and finally bubbles of void trapped inside a continuous nuclear sea, a structure sometimes called Swiss cheese. Blobs, rods, sheets, tubes, bubbles. An entire menu of matter, each shape the most efficient way for the nuclear material to arrange itself at that particular depth and pressure. Now, I have been describing this as matter breaking down, and in a sense it is. The neat individual nuclei we knew up above are gone, merged and stretched into these enormous, continuous structures. But here is the contradiction I asked you to watch for, appearing for the first time. This broken down matter is not weak. It is not a mush. It may be the strongest material in the entire universe. When physicists run simulations of nuclear pasta, modeling how it responds when you try to break it, they find that it is staggeringly, almost unbelievably tough. The best estimates suggest that nuclear pasta is around 10 billion times stronger than steel. 10 billion times. There is nothing else like it anywhere. The hardest, most resilient substance known to exist sits a single kilometre beneath a surface smoother than glass, woven out of nuclei that have forgotten how to be round. Take a moment with that image, because it is one of my favourites in all of physics. If you could somehow stand inside the crust of a neutron star and look around, you would not see a chaotic jumble. You would see a strange, silent, perfectly ordered architecture. Enormous sheets of nuclear matter, stacked like the pages of a frozen book, kilometres across. Bundles of cylindrical rods running in parallel like an impossible forest. Lattices of bubbles trapped in a solid that is harder than anything human hands could ever shape. All of it utterly still, utterly silent, crushed into existence by gravity, lit by nothing, seen by no one. The strongest stuff in creation, hidden in the dark beneath the skin of a dead star, and the strength matters for a reason that will become important very soon. A material this rigid, this strong, can hold enormous amounts of stress without breaking. It can be stretched and strained and twisted by the immense forces inside the star, and it will hold and hold and keep holding, storing up that strain like a spring being wound tighter and tighter. Which means that when it finally does give, when the stress finally exceeds even what nuclear pasta can bear, something has to happen. The stored energy has to go somewhere. And remarkably, astonishingly, that something is occasionally visible to us, light years away, as a tiny stutter in the rhythm of the star. There is something else worth sitting with about nuclear pasta, because it reframes what the word breakdown even means. We tend to imagine that when you destroy a structure, you get rubble, fragments, disorder. But matter in the inner crust does not break into rubble. It flows into new and elegant geometries, each one a precise solution to the problem of how to pack, charge, and nuclear matter together at that exact depth. The transition from blobs to rods to sheets is not a descent into mess. It is a sequence of careful rearrangements, nature finding the single best shape at every level of pressure, the way water finds its level or a soap film finds the smoothest surface. The matter is being broken down from the familiar, yes, but it is being rebuilt into forms that are, in their own alien way, exquisitely organized. This is the same lesson we will keep relearning all the way down, the lesson that crushing matter does not simply ruin it, but transforms it into stranger and often more ordered things. And it is humbling to remember that we have never seen any of this. No instrument has ever imaged nuclear pasta. No sample of it sits in any laboratory, and none ever will, because the moment you removed it from the crushing pressure of the star, it would explode back into ordinary matter in an instant. Everything we know about this substance, its shapes, its staggering strength, its role in starquakes, comes from theory and from computer simulations, from physicists modeling the war between the nuclear and electric forces and watching the pasta shapes emerge in their equations. It is a material we are confident exists by the billions of tons, a kilometre beneath the surface of objects scattered across the galaxy, and yet it is a material no human eye has ever beheld or ever will. The inside of a neutron star is full of such things, certainties we can never visit. The density here, by the way, has been climbing the entire time. Across this 1 kilometre of crust, from the outer edge to the bottom of the inner crust, the density rises by a factor of millions, even though, by the standards of a star, the temperature barely enters into it at all. This is cold physics, in a strange sense, physics driven not by heat, but by sheer crushing weight. We are nearly at the density of an atomic nucleus now, the density inside the very center of an atom, and we are about to cross a threshold where the crust ends and the core begins, where even these pasta structures dissolve and matter becomes something smoother and stranger still. But before we cross that boundary, I want to pause on that stored stress, on the strain wound up in the strongest material in the universe, because it gives us something rare and precious in this whole descent. It gives us a way to actually hear the inside of a neutron star, not see it, hear it, in a sense. Because the breakdown of matter down here, hidden as it is, has a heartbeat, and that heartbeat reaches us across the dark. Is less than break time equals 1s, is greater than number, part 5, starquakes. The heartbeat we can actually hear. Many neutron stars are pulsars, which means they spin, often astonishingly fast, sweeping beams of radiation around like a lighthouse, and as those beams flick across the Earth, we detect them as pulses, regular as a metronome, and these are some of the most precise clocks in the universe. A pulsar can spin hundreds of times per second and keep time so reliably that it rivals the best atomic clocks humanity has ever built. We can predict their ticks years in advance, down to fractions of a microsecond, which is exactly why it is so remarkable when one of them suddenly skips. Every so often, astronomers watching a pulsar see it spin abruptly jump, speeding up by a tiny but unmistakable amount, in an event called a glitch. The clock, which had been ticking with impossible regularity, suddenly lurches forward, as if something inside it had shifted, and from light years away, With nothing but radio telescopes, we can time that lurch with extraordinary precision. What causes it? We cannot see inside, so we have to reason from the physics, and there are two leading explanations, both of which depend entirely on the layered, stressed, superfluid structure we have just been falling through. The first is the starquake. Remember that incredibly strong, incredibly strained crust that nuclear pasta wound up like a spring. As the star spins, and especially as a young pulsar gradually slows over time, the shape of the star needs to adjust, and stress builds in the rigid crust. Eventually, that stress exceeds what even nuclear pasta can hold, and the crust fractures and shifts, suddenly settling into a slightly more compact shape. And just as a spinning skater speeds up when they pull their arms in, the star spins faster when its crust suddenly tightens. A starquake, an actual fracturing of the strongest material in the universe, felt across the galaxy as a hiccup in a clock. The second explanation reaches even deeper into the superfluid we met among the pasta. That frictionless neutron superfluid does not slow down the way the solid crust does. It keeps spinning at its own rate, storing rotation, gradually falling out of step with the slowing crust around it. And then, all at once, it couples back to the crust and dumps its stored rotation into it, giving the whole star a sudden kick. Either way, whether it is the crust cracking or the superfluid lurching, a glitch is a direct message from the hidden interior, a signal that the strange layered structure we have been describing is not a frozen diagram in a textbook, but a living, straining, occasionally shifting thing, and I find that genuinely moving in its quiet way. We cannot send a probe into a neutron star. We cannot shine a light down through its layers. The interior is sealed away from us as completely as anything in nature. And yet the breakdown of matter down there has a pulse, a faint and irregular heartbeat that we can detect and time and study from unimaginable distances, using nothing but the rhythm of the star's own light. Every glitch is the ladder of broken-down matter shifting under strain, the crust and the superfluid and the pasta readjusting their impossible architecture. It is the closest thing we have to actually feeling the inside of one of these objects. And it is the last clear signal we are going to get. Because below the crust, past this boundary we are about to cross, we fall into regions from which no such message escapes, regions we can only reach with theory and inference, where the descent becomes a journey almost entirely into the unknown. Is less than break time equals 1s? Is greater than number, part 6, the sea with no friction. We have reached the boundary between the crust and the core, and as we cross it, the last of the solid structure dissolves away beneath us. The lattice of nuclei, the pasta shapes, the rigid architecture of the crust, all of it gives way, and matter becomes uniform, smooth, continuous. We have entered the outer core of the neutron star, and we are now inside the largest part of the object by mass, the region that makes up the bulk of everything the star is. What is it made of? Overwhelmingly, neutrons. This is, after all, a neutron star, and here in the outer core we finally reach the substance the name promises, a dense, uniform fluid of neutrons, packed at and above the density of an atomic nucleus. But not pure neutrons. Mixed in among them is a small minority of protons, perhaps 10% or so, along with enough electrons and muons, which are heavier cousins of the electron, to keep the whole thing electrically balanced. This mixture, this neutron-dominated fluid with its sprinkling of other particles, is what most of a neutron star actually is. Not a solid, not a gas. A liquid of a kind, denser than anything else that holds together in the universe. And it is here that the matter does something I genuinely struggle to find words large enough for. The neutrons, packed this tightly, and this cold, pair up with one another and become a superfluid. Now, We touched on superfluids up among the pasta, but I want to slow down and really sit with what a superfluid is, because it is one of the most beautiful states matter can take. A superfluid flows with exactly zero friction. Not low friction, zero. If you could set a superfluid swirling in a container, it would swirl forever, never slowing, never running down, because there is no internal friction to drain away its motion. It is a liquid that has, in a sense, escaped one of the basic taxes of the physical world, the slow loss of energy to friction that brings everything else eventually to rest. And the entire outer core of a neutron star, a sphere of neutron fluid, many kilometers across, is thought to be exactly this, a frictionless quantum sea, big enough to swallow a city, swirling without resistance in the dark. The protons do something equally strange. That minority of protons pairs up too and becomes a superconductor, which is the electrical cousin of a superfluid, a state that carries electric current with zero resistance and does extraordinary things to magnetic fields. And this matters because neutron stars have some of the most powerful magnetic fields in the universe, trillions of times stronger than Earth's, and it may be this proton superconductor in the outer core that organizes and sustains that titanic magnetism. So the core is, all at once, a frictionless fluid and a perfect conductor, a superfluid and a superconductor occupying the same space, a quantum state of astonishing order on a scale of kilometers. And here, I think, is the moment to confront the great contradiction of this whole descent head-on, because it has now become impossible to ignore. We have been falling through matter that is being crushed harder and harder, broken down further and further from anything ordinary. And the naive expectation, the intuition almost everyone starts with, is that this should produce more chaos, more mess, more disorder. But look at what we have actually found. The deeper we go, the more ordered the matter becomes. A superfluid is not a chaotic state. It is one of the most coherent, most organized states of matter that exists, a state in which countless particles stop behaving as separate individuals and start moving together as a single quantum entity. The whole outer core, this sea of neutron superfluid and proton superconductor, behaves less like a crowd of particles and more like one enormous, coherent quantum object, the size of a city, all of it moving and responding as a unified whole. Think of it this way. Up on the surface, matter was a jumble of separate atoms, each doing its own thing. Down here, the distinction between individual particles has begun to blur into a single shared quantum state. It is as if, as we descend, matter is slowly forgetting how to be made of separate pieces and remembering how to be one thing. The breakdown is not a descent into disorder. It is a descent into a deeper and stranger kind of order, an order so complete that the entire core acts as a single object. And remember those glitches, those stutters in the pulsar's rhythm we listened to a moment ago. This is the very superfluid suspected of causing them, this frictionless sea, storing its rotation and occasionally lurching back into step with the crust above. The thing we heard as a faint heartbeat from light years away is this silent, swirling ocean making itself known. We are now at or just above the density inside an atomic nucleus, but spread across an entire star. And that leads to a reframing so staggering that I want to state it as plainly as I can. A single atomic nucleus is the tiniest speck imaginable, far too small to ever see. But the matter in the core of a neutron star is at that same density, the density of nuclear matter, extended across a sphere kilometers wide. Which means that, in a very real sense, the entire core of a neutron star is a single, gigantic atomic nucleus, the size of a city, held together not by the strong force alone, the way a normal nucleus is, but by the crushing weight of gravity. The whole object is one colossal nucleus. We have turned the smallest thing in nature into something the size of a town. Let me linger here for just a moment longer, because this outer core is the part of a neutron star we understand best, and I want you to appreciate the quiet strangeness of it before we descend into the parts we understand worst. Everything around you right now, the air, the walls, your own body, is held together by the electromagnetic force, by electrons and chemistry, by the gentle agreements between atoms. Down here in the outer core, chemistry has no meaning at all. There are no atoms to do chemistry with. There are no molecules, no compounds, no elements in any sense you would recognize. There is only this single uniform fluid, neutrons and a whisper of protons and electrons, bound together not by chemistry, but by the raw, strong force and the crushing hand of gravity. It is matter stripped down to a far more primitive and fundamental level than anything in your experience, and yet it is not chaotic. It is calm. It is ordered. It flows in perfect silence, a frictionless sea that has been swirling in the dark since before the first complex life appeared on Earth, and will go on swirling long after. And consider how little of this we will ever touch directly. The outer core makes up the bulk of the star, the great middle of everything, and even it is forever beyond our reach. No probe will ever sample it. No light will ever escape from it to show us its face. We know it is a superfluid, we know it is a superconductor, we know it behaves as a single coherent quantum object, and we know all of this without ever having seen it, reasoning it out from the physics, and confirming it through those faint glitches in the pulsar's beat. We have come to know the inside of a star, the way you might come to know the inside of a sealed box, by its weight and its sound, and the rules it must obey, never by opening it. And the deeper we go from here, the more that is true, until knowledge itself begins to give way. But we are not at the bottom yet. Not even close to understanding it, because below this outer core, as we keep falling, and the density keeps climbing past several times the density of a nucleus, we reach the inner core, the deepest region, the sealed room at the very core of everything. And here, the neutrons that have defined this entire object begin to run out of room. The rules that have held them apart this whole way down begin to strain. And our physics, the proud and powerful theory that has carried us this far, begins, for the first time, to go blind. Is less than break time equals 1s is greater than number, part 7. When neutrons run out of room, we have arrived at the inner core, and I need to be honest with you about something as we step into it. This is the region where the scientists stop agreeing. Up until now, everything I have described to you is reasonably well understood, supported by solid theory and constrained by observation. The crust, the pasta, the superfluid outer core, these are not wild guesses. But here, in the inner core, where the density climbs to several times that of an atomic nucleus, the confident map runs out. Every theoretical model of what happens here disagrees with every other one. We are entering the part of the star that physics argues about. Let me explain why. Because the reason is itself fascinating, and it goes right back to the Pauli exclusion principle we met at the very beginning. Remember that the neutrons refuse to share quantum states, and that refusal produces a pressure that helps hold the star up. But that refusal comes at a cost. Every time you force the neutrons closer together, you push them into higher and higher energy states, and that takes more and more energy. Down here in the inner core, the neutrons are packed so ferociously tight that the energy cost of squeezing them any further is becoming astronomical. They are, in a very real sense, running out of room. The cheap, easy space has all been used up. Every additional bit of compression now demands an enormous price. And this puts the matter in a kind of crisis. A crisis that nature has to resolve somehow. When the energy cost of staying as neutrons gets high enough, it can actually become cheaper, more energetically favorable, for the matter to do something drastic, to stop being neutrons, to rearrange itself into some entirely different form that sidesteps the crushing cost of the Pauli principle. and that is the central drama of the inner core. The matter is looking for an escape route, a way to relieve a pressure that has become almost unbearable, and there are several possible escape routes it might take. The trouble is, we do not know which one it actually takes, because the physics that governs the choice is physics we cannot currently solve. Everything hinges on something physicists call the equation of state, and I want to make sure you understand what that means, because it is the single most important unknown in this entire subject. The equation of state is, at its core, a simple relationship. It tells you, for a given density, how much pressure the matter pushes back with. That is all. How hard does this stuff resist being squeezed? And from that one relationship, that one curve of pressure against density, everything else follows. The maximum mass a neutron star can have before collapsing, its radius, its internal structure, its ultimate fate. If we knew the equation of state of matter at these extreme densities, we would essentially know the answer to tonight's question, and we do not know it. The equation of state of ultra-dense matter is one of the great open problems in modern physics. There is a useful way to think about it in plain language. We talk about matter being stiff or soft. Stiff matter resists compression fiercely. You push on it, and it pushes back hard, refusing to be squeezed much at all. Soft matter yields. You push on it, and it gives way, compressing more easily. And this distinction has enormous consequences. Stiff matter can support a very heavy neutron star because it pushes back hard enough to hold up a lot of weight. Soft matter caps the mass at a lower value because it yields under the load. So when we measure how massive neutron stars can actually get, we are, in effect, measuring how stiff or soft the matter inside them is. Nature is running the experiment for us, and we are reading the results in the sky. And this is where observation comes back to rescue us, at least partway. We have measured some of these stars with real precision. The instrument NICER, watching from the International Space Station, studied a pulsar called J0740+6620, which is one of the most massive neutron stars we know of, weighing in at about 2 800 times the mass of the Sunday. And NICER measured its radius to be somewhere near 12 4/10 kilometers. Now think about what that combination means. More than 2 solar masses of material crushed into a ball, only about 12 kilometers in radius, and it has not collapsed. It is holding. And the only way it can be holding is if the matter inside it is stiff enough to support all that weight at that density. That single measurement, that one heavy star with its precisely measured size, places a powerful constraint on the equation of state at a few times nuclear density. It tells us the matter down there pushes back hard. It rules out the softest possibilities. It is one of the most valuable clues we have about the sealed room at the center. But a clue is not an answer, and here is the deeper problem, the one that makes the inner core such a profound mystery. Our theory of the strong force, the force doing all the real work down here, is called quantum chromodynamics. And quantum chromodynamics, magnificent as it is, cannot actually be solved under these conditions. At low energies, the strong force is what physicists call non-perturbative, which means the usual mathematical tricks for getting approximate answers simply break down. The equations are there. We wrote them down decades ago, but we cannot solve them for the cold, dense matter inside a neutron star core. There is a powerful numerical method called lattice quantum chromodynamics that lets physicists simulate the strong force on supercomputers by chopping space and time into a grid and grinding through the calculation. And it works beautifully for some situations. It works for the hot, dense matter of the early universe, for instance. But it suffers from a notorious obstacle, known as the sign problem, that strikes precisely under the conditions we care about, the cold and dense conditions inside a neutron star. The calculation, under exactly these circumstances, falls apart into a haze of competing positive and negative numbers that cancel each other into uselessness. So we have the right theory. We have the equations of the strong force, confirmed in countless experiments. And the one regime where we most desperately want to use them, the core of a neutron star, is the one regime where our methods for solving them fail us completely. Sit with the strangeness of that for a moment. We are not lost here because we lack a theory. We are lost because the theory we have, the correct one, becomes unsolvable at exactly the place we need it most. It is like owning a perfect map of a country, written in a language that becomes unreadable precisely over the one city you are trying to reach. The neutrons are running out of room. The matter is straining towards some new form, and our finest physics stands at the threshold of the inner core and confesses that it cannot calculate what waits inside. And I want you to notice something about how we are reasoning here, because it tells you a lot about how this whole science works. We cannot calculate the answer from first principles, so instead we triangulate. We take what nuclear physics can tell us about matter just below the inner core, where our theories still hold, and we treat that as a floor we must build up from. We take what quark physics can tell us about matter at the very highest densities, where the strong force finally weakens enough to handle, and we treat that as a ceiling we must connect down to. And then we ask what kinds of matter could possibly bridge the gap in between, in the unknown middle, while still matching every star we have ever weighed and measured. It is a little like knowing the bottom of a mountain and the top of a mountain in fine detail, while the middle is lost in cloud, and trying to deduce the shape of the slope you cannot see. The masses and radii of real stars are the few fixed pegs driven into that hidden middle, and every candidate model has to thread itself between them. That is the strange, indirect, and quietly beautiful way we study a place we can never visit. So we are left to consider the possibilities, the candidate escape routes the matter might take. And before we reach the most radical one, the one this whole descent has been falling toward, we need to meet the gentler options first, the ways the matter might rearrange without fully dissolving. Because those gentler options come with a puzzle of their own, a puzzle that has frustrated physicists for years, and that puzzle turns out to be one of the strongest hints that something far stranger is going on at the very center. Is less than break time equals 1s. Is greater than number. Part 8. Hyperons, condensates, and the hyperon puzzle. Let us begin with the most natural escape route the matter might take, the one that does not require anything as dramatic as the neutrons coming apart. To understand it, you need to know that the neutron has heavier relatives. The neutron is built from quarks, 3 of them, 2 down quarks and 1 up quark, bound together by the strong force. But quarks come in more varieties than just up and down. There is a heavier kind, called the strange quark, and if you take a neutron and replace one of its quarks with a strange quark, you get a different, heavier particle. These heavier cousins of the neutron, the particles that contain one or more strange quarks, are called hyperons. Now, normally, hyperons are unstable and irrelevant to everyday matter. They are heavier than neutrons, and nature does not like to make heavy particles when light ones will do. It costs energy to make a hyperon, and so under ordinary conditions, none exist. But remember the crisis in the inner core. The neutrons are running out of room, and the energy cost of cramming them any tighter is becoming enormous. And at some point, that cost can become so high that an alternative starts to look attractive. It can actually become cheaper, energetically, to convert some of those over-squeezed neutrons into hyperons, even though hyperons are heavier, because turning into a hyperon lets the particle escape the crushing, poorly crowding that the neutrons are suffering. The matter pays the price of the hyperon's extra mass in order to relieve a pressure that has become even more expensive. So in the inner core, the theory says some fraction of the neutrons may transform into these strange, heavy cousins. There are other possibilities along similar lines. Some models predict that the core might fill with what is called a pion condensate or a kaon condensate, where particles called mesons accumulate and pile into a single shared quantum state, much as the neutrons did when they became a superfluid. These are different ways for the matter to reorganize itself, to find a lower energy arrangement than simply staying as crushed neutrons. And notice that strangeness keeps appearing. The strange quark, that heavier building block, keeps showing up as part of the escape route. That is a hint, a quiet foreshadowing of what may dominate at the very bottom, and I want you to keep it in the back of your mind. But here is where it gets genuinely puzzling, and this puzzle has a name. It is called the hyperon puzzle, and it has bothered physicists for years. When you put hyperons into your model of the inner core, something goes wrong. The hyperons relieve the pressure, yes, but in doing so, they make the matter softer. Remember, stiff and soft. By giving the neutrons an escape route, the hyperons let the matter yield more easily under compression. The equation of state goes soft, and soft matter, as we said, cannot support a heavy neutron star. When physicists build models with hyperons in the core, those models predict that neutron stars should collapse at masses well below 2 times the mass of the Sunday. And that is a disaster, because we observe neutron stars heavier than 2 solar masses. We have measured them, they are out there, holding themselves up, refusing to collapse. So the theory and the observation are in direct conflict. The theory says hyperons should appear and soften the matter and cap the mass below 2 solar masses. The sky says neutron stars can be heavier than that. Both cannot be right. Something is missing from the picture. This is the hyperon puzzle, the contradiction between what our models of the inner core predict and what the universe actually shows us. So physicists have to find a way out, and there are several proposals. Perhaps there is some additional repulsion between the hyperons that we have not accounted for, some extra push that stiffens the matter back up and rescues the missing mass. Perhaps there are subtle 3-body forces, interactions involving 3 particles at once, that provide the needed support. Or perhaps, and this is the possibility that the whole descent has been building toward, the resolution is something far more dramatic. Perhaps the matter does not stop at hyperons at all. Perhaps, at these densities, it takes the most radical escape route of all, the one where the neutrons and the hyperons and everything else simply come apart, where the very particles dissolve and release what is inside them. It is worth pausing to appreciate just how much rides on those measured masses, because this is where the abstract theory meets the hard reality of observation, and the two are locked in a kind of conversation. Every time astronomers weigh a neutron star with precision, they are not just adding a number to a catalogue, they are testing every model of the inner core at once. A single confirmed heavy star, one that tips the scale above 2 solar masses, sweeps an entire family of theoretical models straight into the dustbin, all the soft ones, all the ones that predicted collapse at lower weights. When the pulsar called J0740 was confirmed at more than 2 solar masses, it did exactly that, ruling out whole categories of soft equations of state in a single stroke. So, the hyperon puzzle is not a quiet academic disagreement that nobody can settle. It is a sharp, falsifiable conflict, refereed by real stars in the real sky, and the stars keep siding against the simple hyperon picture. Nature has weighed in, quite literally, and it is telling us that whatever fills the inner core, it has to stay stiff, stiffer than hyperons alone would allow. And there is a deeper hint folded into all of this, one I do not want you to miss. Notice how the strange quark keeps forcing its way into the story. It appeared in the hyperons, those heavy, strange cousins of the neutron. It will appear again, more fully, at the very bottom. It is as if, the harder we crush matter, the more strangeness wants to enter, the more the universe reaches for that third kind of quark that ordinary matter never uses. That is not a coincidence, and it is not a small detail. It is a signpost. The matter is trying to tell us where it wants to go as the pressure climbs, and the direction it keeps pointing is toward strangeness, toward quarks set loose, toward the floor we are about to reach. The hyperons are a halfway house, the matter dipping a toe into strangeness while still keeping its particles intact. But the pressure is not done climbing, because everything we have seen so far, all the way down through this descent, has been matter rearranging its particles. The atom dissolved, but the nuclei remained. The nuclei dissolved into pasta, but the neutrons remained. The neutrons became a superfluid, but they were still neutrons. At every floor, the building blocks reshuffled, but the fundamental pieces stayed intact. Now, in the inner core, we are reaching the threshold of something genuinely new. Not a reshuffling of the particles, but the breakdown of the particles themselves. And what is inside a neutron, what comes pouring out when a neutron finally comes apart, is the strangest and most fundamental thing we will encounter in this entire journey. We are about to watch the neutron dissolve. Is less than break time equals 1s, is greater than number. Part 9 Deconfinement. The neutron dissolves. This is the floor the whole descent has been falling toward. Everything before now has been preparation for this moment, the moment when matter takes its final and most radical step away from anything we know. So, let me set it up carefully, because it requires understanding one of the deepest and most surprising facts about how reality is built. A neutron is not a fundamental particle. It is made of smaller things, 3 quarks, bound together by the strong force. And the strong force does something to those quarks that no other force in nature does to anything. It imprisons them, completely, permanently. Under all ordinary conditions, you can never, ever get a single quark on its own. This is one of the strangest rules in physics, and it is called confinement. The quarks inside a neutron are locked together so tightly that they cannot be separated, no matter how hard you try. And here is the truly bizarre part. The strong force does not behave like any force you have an intuition for. Gravity gets weaker as things move apart. The electric force gets weaker as charges move apart. Everything in your everyday experience weakens with distance. But the strong force between quarks does the opposite. The farther apart you try to pull 2 quarks, the harder it pulls them back. It is like a rubber band, or a spring that gets stronger the more you stretch it. And if you pull hard enough, if you put enough energy into trying to separate 2 quarks, that energy does not free them. Instead, it gets converted by the famous relationship between energy and mass into a brand new pair of quarks, which immediately bind to the ones you were trying to separate. You end up with more particles, not free quarks. Nature simply refuses to let a quark exist alone. Pull a quark out of a neutron, and you just make new neutrons or other particles, but never a lone quark. The prison is absolute. So how could the neutrons ever dissolve if their quarks can never be freed? The answer lies in the other half of this strange behavior, a discovery so important it won the Nobel Prize in Physics in the year 2004, awarded to David Gross, David Politzer, and Frank Wilczek. They showed that while the strong force gets stronger as quarks move apart, it gets weaker as quarks are pushed closer together. This is called asymptotic freedom. When quarks are crammed extremely close to one another, packed into a tiny space at enormous density, the strong force between them actually fades. The grip loosens. The prison bars, in a sense, soften. And now you can see the escape route the matter has been searching for. Down here, in the inner core of a neutron star, the density is so unimaginable that the neutrons are crushed together until they are practically overlapping. And when neutrons are squeezed that close, their quarks are no longer confined to their own individual neutrons. The quarks from one neutron are as close to the quarks of the next neutron as they are to their own neighbors. The walls between the neutrons stop meaning anything The neutrons lose their individual identities entirely, and their quarks spill out and merge into a single, shared, continuous sea. This is deconfinement. This is quark matter. The building blocks that were locked away inside every neutron since the dawn of time are now, for the first time, free to roam, not because we pulled them apart, but because we crushed them so close together that the prison itself dissolved. I want you to picture the transformation, because it is one of the most extraordinary things in all of physics. A moment ago, you had a fluid of distinct neutrons, each one a tidy little package of 3 quarks, jostling against its neighbours. Now, all those packages have burst open at once, and what you have instead is an ocean. A continuous ocean of quarks, and the gluons that carry the strong force between them, flowing as one substance, with no walls, no individual particles, no neutrons left at all. The matter that defines the star, the neutrons it is named for, has dissolved into something more fundamental, something that has no everyday name, because nothing in your world has ever been anything like it. And here is what gives me genuine chills every time I think about it. This state of matter, free quarks roaming loose, has not existed naturally in the universe for nearly 14 billion years. The only other time the cosmos was filled with free quarks was in the first few millionths of a second after the Big Bang, when the entire universe was so hot and so dense that quarks could not yet bind into particles. As the universe cooled, those quarks locked themselves away inside protons and neutrons, and they have stayed locked away ever since, in every atom of every star and planet and person, for 13.8 billion years. And yet, possibly, in the hearts of these dead stars, the prison opens again. The quarks run free once more, for the first time since the universe was newborn. The center of a neutron star may be the one place in all of creation where the conditions of the first microsecond after the beginning of everything are recreated and held stable and waiting in the dark. Now, how confident are we that this actually happens? This is where I have to be careful and honest, because this is the frontier, and the frontier is where certainty thins out. We cannot see into the core. We cannot run the equations of the strong force at these densities, as we discussed. So everything here is inference, careful reasoning from indirect evidence. But that evidence has been growing, and growing in a particular direction. In recent years, physicists have taken all the data we have, the masses of neutron stars, their measured radii from instruments like NICER, the ripples in space-time from neutron stars colliding, and they have asked a statistical question. Given everything we observe, which is more likely, that the cores of the heaviest neutron stars are made of ordinary neutron matter, or that they contain a core of deconfined quark matter, and as of recent analyses in 2025, the answer is coming back in favor of quark matter. The statistical odds favor the presence of quark cores in the most massive neutron stars, and by a considerable margin for the fullest sets of data. Earlier work, going back several years, had already suggested that the heaviest neutron stars should host sizable quark cores, regions of deconfined matter at least several kilometers across, sitting at the very center. So the leading interpretation right now, the one the evidence increasingly points to, is that the most massive neutron stars are not entirely neutron stars at all. They are hybrid objects, with an outer mantle of neutron matter wrapped around an inner core of free quarks. And this also, beautifully, helps resolve the hyperon puzzle we struggled with a moment ago. Remember that the matter needed something to stiffen it back up, to rescue the missing mass that the hyperons had softened away. Quark matter, under the right conditions, can provide exactly that stiffness. The transition to quark matter can keep the star strong enough to reach the 2 solar mass weights we observe. The most exotic possibility turns out to be the one that makes the numbers work. There is a lively debate about exactly how the change happens, and it is worth understanding because it changes the picture of the star's interior in a fundamental way. One possibility is a sharp transition, what physicists call a first-order phase transition. In this picture, there is an actual boundary inside the star, a literal surface, with ordinary neutron matter on one side and deconfined quark matter on the other, the way there is a sharp surface between ice and the water it floats in. Cross that boundary as you descend, and the matter changes its nature abruptly, all at once. The other possibility is a smooth crossover, where there is no sharp boundary at all, and the neutron matter gradually, continuously morphs into quark matter as the density rises, with a wide zone in between where the matter is some ambiguous mixture of both, neither fully neutrons nor fully free quarks. We do not yet know which picture is correct, and physicists are actively searching for the fingerprints of each, including in the gravitational waves that ripple out when two neutron stars collide and their cores are crushed together. I have to keep stressing the uncertainty because it would be dishonest not to. None of this is a photograph. No one has seen a quark core. It is all reconstruction, inference, the careful weighing of indirect clues, statistical arguments built on measurements taken from light years away. It is strongly suggestive. The evidence leans, and leans increasingly hard, toward quark matter at the center of the heaviest neutron stars. But it is not yet settled, and an honest guide has to tell you that the sealed room remains sealed, even as our best reasoning increasingly tells us what is probably inside. And yet, even granting all that uncertainty, we have reached something remarkable in this descent. We have fallen through the atom, through the nucleus, through the neutron itself, and we have arrived at matter with no name, a free quark sea that last filled the universe in its first instant. We have reached the floor the title promised, the place where matter finally finishes breaking down. But the strangest thing of all is still ahead of us. Because that free quark sea, that final and most broken down form of matter, does not stay a featureless soup. It does something with itself. It organizes. And what it may organize itself into is, I think, the most beautiful and paradoxical idea in this entire story. The final return of that contradiction I asked you to watch for at the very start. The most broken matter in the universe may also be the most perfectly ordered. Let me show you how. Is less than break time equals 1s is greater than number part 10. The most broken, the most perfect. We have dissolved the neutrons. We have reached the free quark sea at the bottom of the descent, the deconfined matter that the whole of tonight has been falling toward. And now we ask the question that turns this from a story about destruction into a story about something far stranger. What does that quark sea actually do? Because matter, even matter this broken, does not simply sit there as a uniform mush. It seeks out the lowest energy arrangement it can find. It organizes, and to understand what the quark sea organizes itself into, I want to take you on a brief detour through one of the most useful and beautiful ideas in all of physics, an idea that connects the core of a dead star to a phenomenon you may have a coil of in your own home. Have you ever heard of a superconductor? It is a material that carries electricity with absolutely no resistance, no loss, no friction for the flowing current. We use them in the most powerful magnets humanity builds, in medical scanners and particle colliders. And the reason a superconductor works is genuinely strange and quantum. Inside an ordinary wire, electricity is carried by electrons, and those electrons constantly bump into things and lose energy, which is electrical resistance. But in a superconductor, cooled below a certain temperature, something remarkable happens. The electrons stop travelling as lonely individuals and instead pair up, forming what are called Cooper pairs, two electrons bound together into a single partnership. And once the electrons are paired, they can flow in perfect coordination, slipping through the material without resistance, without loss, forever. The pairing transforms the matter into a frictionless conductor of electricity. It is one of the deepest and most counterintuitive states matter can take. Now hold that idea. Electrons pairing up to become something perfectly ordered and frictionless, and bring it down into the quark sea at the center of our neutron star. Because the quarks down here can do exactly the same thing. At the staggering densities of the inner core, the quarks, like electrons in a superconductor, can pair up with one another. And when they do, the quark matter becomes a superconductor too, but a superconductor of a far more exotic kind, because quarks carry not just electric charge, but also the strange property that the strong force responds to, a property physicists whimsically named color. It has nothing to do with actual color, of course. It is just the name for the kind of charge that the strong force feels, the way electric charge is what the electric force feels. And so when quarks pair up at the core of a neutron star, the resulting state is called a color superconductor. The most broken down matter in the universe spontaneously organizes itself into one of the most ordered states physics can describe. And it gets more beautiful the closer you look. There is not just one kind of color superconductor. There is a whole ladder of them, depending on how dense the matter is and which quarks are participating. At somewhat lower densities, you may get a phase where only the up and down quarks, the ordinary ones, pair up. Physicists call this the two-flavor phase, sometimes shortened to 2SC. But push to even higher densities, the densities at the very deepest center, and the strange quarks, those heavy cousins we kept meeting, join the party too. And when up quarks, down quarks, and strange quarks all pair together in a fully symmetric way, you reach the most ordered state of all, a phase with a name that sounds like poetry once you understand it. It is called the color-flavor-locked phase. Color-flavor-locked. The phrase describes how completely organized this matter is. The color charges and the flavor types of the quarks become locked together in a single, perfectly symmetric pattern. Every quark partnered, every property accounted for, the whole thing woven into one coherent quantum fabric. And this color-flavor-locked matter, this possible final state at the very center of the heaviest neutron stars, has properties that are almost difficult to believe. It is a color superconductor carrying the strong force equivalent of current without resistance. It is, at the same time, a superfluid, flowing without friction the way the neutron sea did far above it, but now built from free quarks. And here is perhaps the strangest feature of all. It is electrically neutral all by itself, with no need for any electrons at all. Up above, in the neutron core, electrons had to be mixed in to balance the charge. But color-flavor-locked matter arranges its quarks so symmetrically that the charges balance perfectly on their own, and the electrons are simply expelled, no longer needed. It is matter that has achieved a kind of self-contained perfection, neutral, frictionless, superconducting, superfluid, all at once, a single coherent quantum object at the center of a star. So let me state the paradox as plainly as I can, because this is the contradiction I have been asking you to watch for since the very first minutes of our descent, and here it is in its fullest form. We started at the surface with ordinary matter, atoms doing their ordinary business. We crushed it, and it broke down. The atoms dissolved. The nuclei dissolved. The neutrons dissolved. We have arrived at the most broken down matter in the entire universe, quarks torn free from the particles that imprisoned them for 14 billion years. And what is this most broken matter? It is the most perfectly ordered, most symmetric, most coherent state that physics knows how to describe. Breaking matter down to its absolute limit does not produce chaos. It produces a flawless quantum crystal of liberated quarks, the most organized thing the universe may be capable of making. Destruction and perfection turn out to be the same place. The bottom of the descent is not a ruin, it is a cathedral. Now, I have been describing this with a confidence that I have to immediately qualify, because color-flavor-locked matter, as gorgeous as the theory is, has not been confirmed to exist in any real star. It is the leading candidate for the identity of the very bottom, the front-runner, in a field of possibilities, but it remains a theoretical prediction. And so the most exciting recent work has been the effort to actually test it, to drag this idea out of pure theory and confront it with real observations, and that work has been bearing fruit. In 2025, physicists managed, for the first time, to place an empirical bound on how strongly the quarks pair in this color superconducting matter using real data, combining the X-ray measurements from NICA, the gravitational wave detections from the great observatories that listen for colliding neutron stars, and the precise timing of radio pulsars. For the first time, telescope data was reaching down and constraining the microscopic physics of how quarks pair at the center of a star. The sealed room is still sealed, but we have begun, faintly, to measure the shape of what is inside it. And there was an even more remarkable result, one that flips our intuition entirely. You might think that this exotic color superconducting quark matter, being so strange and so remote, would be a fragile curiosity, almost beside the point. But recent work, reported toward the end of 2025, suggested something remarkable. The energy released when the quarks pair up, the binding energy of the color superconductor, may actually provide extra support to the star. It may stiffen the matter, push back a little harder against gravity, and in doing so, help explain how the very heaviest neutron stars manage to exist at all without collapsing. Think about what that means in the context of our whole story. The most broken down, most exotic state of matter, the free quark sea at the absolute center, may be precisely what is holding the heaviest of these stars up. The breakdown does not weaken the star toward collapse. In these objects, the breakdown may be the very thing preventing collapse. The dissolution of the neutrons becomes the foundation that keeps the whole structure standing. The theorists have not been idle either. Groups working at institutions in Germany, refining the calculations of how cold, dense quark matter behaves, have pushed the theory to new levels of precision, tightening the predictions for the properties of this matter at the highest densities, narrowing the gap between what nuclear theory can tell us from below and what quark theory can tell us from above. Slowly, from both directions, the bracket around the unknown center is closing. We are squeezing the mystery from both sides, even if we cannot yet open it. And I should tell you that color-flavor-locked matter is not even the end of the strangeness. Physicists have mapped out, in theory, a whole array of possible quark phases, an entire zoo of exotic states that the matter might take under slightly different conditions. There are crystalline color superconductors, where the paired quarks arrange themselves into repeating patterns like a crystal made of pairings. There are other proposed phases, stranger still, with no analogue anywhere on Earth, states of matter that may exist only in the hearts of these stars and nowhere else in all of creation. The inside of a neutron star may host a form of matter so exotic that we do not even have a way to picture it, only equations that hint at its existence. Let me bring it back to something you can hold in your mind as you drift, because the picture, once you assemble it, is strangely peaceful. Imagine, at the very center of a dead star, a sphere of quark matter a few kilometers across. It flows without any friction at all, forever, never slowing. It conducts the strong force without resistance. It is, in its perfect symmetry, more ordered than any crystal, more coherent than any material you have ever touched. And it is utterly silent, utterly still in its frictionless flow, sealed beneath kilometers of neutron sea and pasta and crust, lit by nothing, touched by nothing, holding up the weight of an entire collapsed star on the strength of its own paired quarks. That may be what waits at the bottom of the descent. That may be the answer to the question we started with, the answer to what happens when matter finally finishes breaking down. It reassembles, at the very last, into the most beautiful and ordered thing it is capable of becoming. So we have our candidate. Color-flavor-locked quark matter is the leading guess for the identity of the floor we have been falling toward all night, the place where matter, having broken down completely, puts itself back together into perfection. The question the title asked has, at last, a possible answer, even if it is one we cannot yet reach or confirm. But there is one more turn to this story, one that lifts it out of the realm of a single star and connects it to the largest stage of all. Because this free quark matter, this deconfined state we work so hard to reach by crushing matter to its limit, was not always so rare. There was a time when it filled everything. There was a time when the entire universe was made of it. And that means the bottom of our descent is not just a place, it is a moment from the beginning of time, preserved at the center of a star. Is less than break time equals 1s is greater than. Number, part 11, the other door. I want to widen the lens now. We have spent this whole journey falling into a single object, sinking through the layers of one dead star toward its hidden core. But the free quark matter we found at the bottom is not unique to neutron stars. It is not some local curiosity that only these objects can produce. It is, in fact, one of the most important states of matter in the entire history of the cosmos, because there was a time when everything, all of it, every scrap of matter in the universe, was exactly this. To understand the floor of our descent, we have to leave the star entirely and travel back to the beginning of time. Let us run the history of the universe backward, the way we did at the start when we imagined collapsing the Sunday. Today the universe is cold and spread out, full of stars and galaxies and empty space. But it has been expanding and cooling for nearly 14 billion years, which means that the further back you go, the hotter and denser everything was. Wind the clock back far enough, past the formation of the first stars, past the time when atoms first formed, past even the time when protons and neutrons first assembled, and you reach the first few millionths of a second after the Big Bang. And in those first microseconds, the universe was so hot and so dense that ordinary matter could not exist at all. Protons and neutrons could not form, because the moment any quarks tried to bind together, the ferocious heat blasted them apart again. So the quarks could not be confined. They roamed free, all of them, everywhere, filling the entire universe. This state, the free quark matter that filled the newborn cosmos, has a name. It is called the quark-gluon plasma, a seething soup of quarks and the gluons that carry the strong force between them, the most fundamental form that matter can take. For the first few millionths of a second of existence, this was the universe. Not stars, not atoms, not even particles as we know them, just an ocean of free quarks and gluons, filling all of space at a temperature of trillions of degrees. And then the universe expanded and cooled, and at a certain moment the quarks slowed down enough for the strong force to grab them and lock them away, 3 at a time, into the protons and neutrons that would go on to build every atom of every star and planet and living thing. The prison doors closed, and they have stayed closed for nearly 14 billion years. Now look at what we have found in this story. The quark-gluon plasma of the early universe and the deconfined quark matter at the center of a neutron star are made of the same fundamental thing, free quarks running loose. But they are reached through 2 completely different doors. The early universe reached it by being unimaginably hot. The heat was so intense that the quarks could not bind. But the center of a neutron star is not hot, not in these terms. It is, by the standards of the early universe, almost cold. The neutron star reaches the same free quark state not through heat but through pressure, through sheer crushing density, by squeezing the matter so hard that the neutrons overlap and the quarks deconfine. 2 doors into the same room. One door is fire. The other door is weight. The young universe walked through the door of heat. The dying star is crushed through the door of density. And they arrive at the same place, the same fundamental matter, by utterly different paths. I find this one of the most profound connections in all of physics, and I want to make sure you feel the full weight of it. When we fall to the center of a neutron star and reach the deconfined quark matter, we are not just reaching the bottom of a star, we are reaching back in time. We are touching the same state of matter that filled the entire universe in its first instant. The center of a neutron star may be a frozen relic of the Big Bang, a sample of the conditions of the first microsecond of creation, preserved and held stable, not for a fleeting fraction of a second as it was in the early cosmos, but potentially for billions of years, sealed away in the dark at the core of a dead star. The thing we have been falling toward all night is not only the deepest place in the star, it is the oldest condition in the universe, the matter of the beginning, hidden in the matter of the end. So the descent we have been making is stranger than it first appeared. We thought we were falling through space, through the layers of a star, from surface to center. But we have also, in a sense, been falling backward through time. Each floor we passed took us not only deeper into the star, but further back toward the conditions of the early universe. The crust, the superfluid, the quark sea, down and down and back, until at the very center we touch the first instant of everything. Falling into a neutron star is falling into the past. The geography of the star is also a history of the cosmos, written in layers of crushed matter. And the wonderful thing is that we can study the early universe version of this matter directly here on Earth, which gives us a way to check our ideas about the version hidden in the stars. In enormous machines, particle colliders, like the one at Brookhaven in New York and the Great Large Hadron Collider at CERN in Europe, physicists smash heavy atomic nuclei, gold or lead, into one another at very nearly the speed of light. And in the instant of those collisions, for a span of time almost too short to imagine, they recreate the conditions of the early universe. They make tiny, fleeting droplets of quark-gluon plasma, free quarks running loose for a fraction of a second, before the droplet expands and cools, and the quarks lock themselves away again. We have made the matter of the first microsecond in a laboratory, on purpose, and watched it form and vanish. And when physicists studied that laboratory quark-gluon plasma, they got a shock, one that connects beautifully back to everything we found inside the star. They had expected the quark-gluon plasma to behave like a gas, a thin and chaotic spray of particles, but it did not. It behaved like a liquid, and not just any liquid. It behaved like the most perfect liquid ever observed, a fluid with almost no viscosity at all, flowing with an ease and a smoothness that nothing else can match, the closest thing to a truly frictionless fluid that has ever been measured in a laboratory. Does that sound familiar? It should. Because all the way down inside the neutron star, we kept meeting frictionless order, the neutron superfluid, the color superconducting quark sea, matter that flows without resistance and organizes itself into states of astonishing coherence. And here, in the recreated matter of the early universe, we find the same theme again, the same astonishing smoothness, the same nearly perfect flow. The most fundamental matter in nature, whether reached through the door of heat or the door of density, seems to want to organize itself into something frictionless and coherent and strangely beautiful. There is a way physicists draw all of this together, a kind of map, and I want to describe it for you because it ties the whole picture into one image. Imagine a chart with two axes. Along one axis, you increase the temperature. Along the other, you increase the density. Ordinary matter, the matter of your everyday world, sits down in the corner where both temperature and density are low. The early universe lived up at the top, where the temperature was enormous, and it swept downward and sideways as it cooled, passing from quark-gluon plasma into ordinary matter. The colliders explore the hot corner, pushing the temperature sky-high to make their fleeting droplets of plasma. And the neutron stars explore the other corner entirely, the cold and dense corner, pushing the density to its absolute extreme, while the temperature stays comparatively low. They are mapping out different regions of the same fundamental diagram, the same array of what matter can be. And the deepest, densest corner of that map, the one only neutron stars can reach, is the one corner we cannot yet calculate, the sealed room, the frontier. The colliders have opened the hot door and walked through it. The cold, dense door, the one at the center of the star, is the harder one, and it remains, for now, only partly open. And there is one more way that the matter of the stars speaks to us, a way that may eventually let us tell, from the outside, which door a particular star has gone through. When two neutron stars spiral together and collide, an event we have actually detected through the ripples it sends through space-time itself, the cores of those stars are crushed together in the final moments, with a violence that may push the matter across the threshold into deconfinement. And the gravitational waves that pour out of that collision carry information about how stiff or soft the matter was, about whether quark matter formed, about the equation of state we have struggled with all night. We felt one such collision in 2017, and the way those two stars deformed each other in their final embrace, the precise way they stretched under each other's gravity, told us something about how compact and how dense they truly were, hinting that at least one of them may have harbored quark matter within. And physicists modeling the matter thrown off when quark stars merge have found that such collisions might leave a distinct signature, a fingerprint that could one day let us distinguish a star with a quark core from an ordinary neutron star, just by the light and the ripples the collision sends across the universe to us. I have to keep the honesty here, as I have throughout. The colliders make the hot quark-gluon plasma for certain. That is established, measured, real. The cold, dense quark matter inside neutron stars remains inferred, the harder door, the one we have only begun to push open. But the connection itself, the recognition that the floor of our descent and the first instant of the universe are made of the same fundamental thing, is one of the deepest truths physics has uncovered, and it does not depend on settling the last details. Whatever exactly waits at the center of a neutron star, it is kin to the matter of the beginning. To fall to the bottom of one of these stars is to fall toward the condition the whole universe shared in its first breath. So we have traveled from a single dead star all the way out to the birth of the cosmos and back again, and we have found them joined at the deepest level, the end and the beginning made of the same liberated quarks. But there is still a little further to fall. There are still a few questions waiting beneath even this one. What if the broken down matter we found is not a rare exotic state at all, but the true and natural form that all matter secretly prefers? And what lies one single step below the bottom we have reached, on the last rung of the ladder of collapse, where even the free quarks lose their final stand? Let us take those last steps together, down to the very bottom of the bottom. Is less than break time equals 1s, is greater than number, part 12, the bottom of the bottom. There is an idea, quiet and unsettling, that has haunted the edges of this subject for decades, and I have been saving it for the end because it changes the way you see not just neutron stars, but the chair you are sitting in and the hand you are reading with. We have been treating the free quark matter at the center of the star as something exotic, rare, a strange exception that only appears under the most extreme, crushing imaginable. But what if that is backward? What if the broken down matter is not the exception, but the rule? What if strange quark matter, that soup of up and down and strange quarks all mixed together, is actually the most stable form of matter there is, the true ground state of all matter, and everything you have ever known, every atom, is only a long-lived accident that never found its way down to the real bottom. This is called the Bodmer-Witten hypothesis, named for the physicists who proposed it, and it is one of the most quietly radical ideas in physics. The reasoning goes like this. Ordinary matter is made of up and down quarks, locked into protons and neutrons. But there is that third kind, the strange quark, that keeps appearing whenever matter is pushed to its limits. And it is at least possible, according to this hypothesis, that a mixture of up, down, and strange quarks together, strange quark matter, is more stable, sits at a lower energy, than the ordinary nuclei we are made of. If that is true, then ordinary matter is not the natural resting state of the universe at all. We are not the ground floor. We are perched on a higher floor, held up only because there is no easy way down, a metastable arrangement that has simply never been given the push it needs to convert into the true, lower, stranger state below. And that leads to a thought experiment that is equal parts fascinating and unnerving. And I want to be very clear that it is a thought experiment, almost certainly not a real danger, before I describe it. If strange quark matter really is the true ground state, then a small, stable lump of it, what physicists call a strangelet, could, in principle, act like a seed. If such a strangelet touched ordinary matter, the ordinary matter might convert, falling down into the lower energy strange state, and that conversion could, in theory, spread, turning whatever it touched into more strange matter, the way a single seed crystal can turn a whole supersaturated solution to ice. Physicists have a nickname for this nightmare scenario, borrowed from a science fiction novel. They call it the Ice 9 problem. And when the most powerful particle colliders were being switched on, this exact possibility was raised, soberly examined, and set aside. Because here is the reassuring part. Cosmic rays, natural particles of staggering energy, have been slamming into the moon and into other objects for billions of years, recreating conditions far more extreme than anything we can make. And the moon is still there. The universe is still here. We are still here. If strangelets could trigger a runaway conversion of ordinary matter, it would almost certainly have happened somewhere by now. So, we sleep safe. But the idea lingers, not as a threat, but as a profound and humbling question. What if the matter we call ordinary is only borrowing its stability, and the strange broken-down matter at the core of a dead star is closer to what the universe truly prefers? The hypothesis is not just idle speculation, either. It makes predictions, and astronomers have gone looking. If strange quark matter is the true ground state, then some compact stars might not be neutron stars at all, but strange stars, objects made entirely of strange quark matter from surface to center, rather than just harboring a quark core far inside. And there are real candidates. There is a compact object associated with a remnant called HESS, J1731-347, and it is strange in a very literal way. It appears to be unusually light, only about 3/4 of the mass of the Sun, and unusually small, with a radius of only around 10 kilometers. And those numbers are difficult to explain with ordinary neutron star physics. A neutron star, that light should not be that small, but a strange quark star fits the measurements rather well, and some careful analyses have found real, substantial evidence favoring the strange star interpretation for this object. There is another pulsar, studied with nicer, whose measured size also fits a strange quark star better than an ordinary neutron star. None of this is settled. The community is genuinely divided, and more precise measurements will be needed to know for certain. But it means the unsettling possibility is not merely philosophical. There may be objects in our sky made entirely of the matter we found at the bottom of the descent, stars that are strange all the way through. And now let us take the final step, the one rung below everything we have explored, because the ladder of collapse has one last rung, and it is the place where even the free quarks lose. All through this descent, we have watched matter find new ways to hold itself up: electron pressure, then neutron pressure, then the strong force, then the stiffness of quark matter, each one a new stand against gravity when the previous one failed. But there is a limit to how far this can go. We met it near the very beginning, and now we return to it with everything we have learned. That limit is the Tolman-Oppenheimer-Volkoff limit, somewhere around 2.25 times the mass of the Sun, give or take, depending on the very equation of state we cannot pin down. And past that limit, there is no next rung. Not quark matter, not color-flavor-locked perfection, not anything. Every form of pressure that physics knows has been exhausted. Gravity, patient and relentless, finally wins completely, and the matter collapses through the floor that is not a floor, down into a black hole, where density climbs not to some enormous but finite value, but, as far as our equations can tell, toward infinity, where even the question of what the matter is made of stops having meaning, because there may be no matter left, in any sense we understand, only curvature, only a point where our physics does not just go blind, but ends entirely. So that is the true bottom of the bottom. One step below the deepest, most ordered, most broken down matter in the universe lies not a deeper material, but the end of materials altogether, the black hole, where the descent finally runs out of floors and the very idea of a floor dissolves. The strange matter at the center of a neutron star is balanced on the last ledge before that final fall, held up by the stiffness of its paired quarks, one good push of extra mass away from vanishing, into a place where nothing can be described at all. Let us come back up now, all the way up, out of the dark, and stand for a moment with everything we have seen. We began on a surface smoother than glass, in gravity that could turn a marshmallow into a bomb. We watched the atoms dissolve in the first few 100 meters, their electrons torn away into a roaring sea. We fell through the strongest material in the universe, nuclei reshaped into sheets and rods and bubbles, a frozen architecture harder than anything human hands could make. We crossed into a frictionless ocean of neutron superfluid, kilometers wide, behaving as a single quantum object the size of a city. We reached the inner core, where the neutrons run out of room and our finest theory goes silent. We watched the neutron itself dissolve, its quarks set free for the first time since the universe was newborn. We found that free quark C organizing itself into a state of impossible perfection, the most broken matter becoming the most ordered. And we recognized, in that bottom, the same matter that once filled the whole cosmos, in its first instant, a frozen drop of the beginning of time, sealed in the core of the end of a star. And here is the thing I want to leave you with, the honest truth at the center of all of it. We fell almost all the way down, and we still could not quite touch the bottom. Our deepest theory, the magnificent theory of the strong force that we confirmed in 1,000 experiments, goes dark a few kilometers before the very center. The universe keeps a sealed room at the core of every neutron star, and we can fall and fall and fall, and read the warmth leaking through the walls, and feel the faint heartbeat of the glitches, and weigh the stars and measure their sizes, and reason our way to within a hair's breadth of the answer, and still that last room stays closed. We know there is something extraordinary inside it. We have very good guesses about what. But the final certainty is held back from us, sitting just out of reach, a question mark the size of a city, hidden inside an object we can point to in the night sky. I think there is something fitting in that, something almost gentle. The matter that breaks down inside a neutron star is not foreign matter, not alien stuff from some other reality. It is the same matter the entire universe was once made of, the same matter that locked itself into the protons and neutrons that build every atom, including the atoms that make up you. When you fall toward the center of a neutron star, You are falling toward the question of what everything is made of, underneath everything, at the very bottom. And the fact that we cannot quite read that bottom, the fact that the universe keeps one room sealed at the core of these dead stars, may be the most honest answer the title can have. What happens when matter breaks down inside a neutron star? It becomes, perhaps, the most ordered and ancient thing it is capable of being. And it becomes, just past the reach of our deepest knowing, a reminder that the question of what that final matter truly is quietly, inescapably, the question of what we ourselves are made of too.